Number of 1 bits. Want to impress interviewers with a classic bit manipulation trick? Number of 1 bits, or Hamming weight, is a pattern mastery 100 must-know and a favorite for roles at Google, Microsoft, and anywhere you work close to the metal. This deceptively simple problem reveals who understands how numbers are stored and manipulated at the binary level. Get this one right, and you'll be ready for any bitwise brain teaser they throw your way. Let's break it down. Given a 32-bit unsigned integer, your job is to count how many ones are in its binary representation. For example, the input here is a number where only a couple of bits are set, and we need to count all of them to get the answer. Now, let's assess our approaches. You could shift and check every bit, but that's up to 32 steps for every number. Can we do better? Yes. With Brian Cunningham algorithm, we repeatedly flip the least significant 1 bit to 0 using AND and n-1. This clever trick only loops as many times as there are 1 bits, lightning fast for sparse numbers. Here's the structure. Start a count at 0, while n is not 0. Set n equals n and n-1 to clear the lowest set bit. Increment count. When n is 0, count holds your answer. Let's try to implement it using solution 1. Here we're defining a class named solution. Think of it as the container that holds our method, the toolbox where our Hamming weight function lives. This line declares a public method called Hamming weight. It takes an integer n and returns how many bits in n are set to 1. In simple terms, if you imagine the binary version of n, we're counting how many lights are turned on. Here we create a counter called C. This will keep track of how many 1 bits we find as we inspect the number bit by bit. This line starts a loop that runs exactly 32 times, once for each bit in a standard 32-bit integer. The idea: we examine 1 bit at a time, starting from the least significant bit and working our way through all 32 positions. Since this loop always runs 32 times, the time complexity is O1, constant time, because it never depends on the size of the input, only the fixed number of bits. This line checks the very last bit of n. n and 1 isolates the least significant bit. If the last bit is 1, the result will be 1. If the last bit is 0, the result will be 0. Then, n and 1 equals 0 asks, is that bit turned on? If yes, we increase our counter C by 1. This line shifts the bits of n1 place to the right using the unsigned right shift operator. Unsigned means we're filling the leftmost position with a 0 regardless of whether the number is positive or negative. By shifting right, we essentially throw away the bit we just looked at and move the next bit into position so we can check it on the next loop iteration in the integer. At this point, C holds the number of 1 bits we found. We return that value. That's the Hamming weight of the number. And that's how this algorithm works. It first initializes a counter, then scans all 32 bits of the number, checking each bit and shifting the number step by step until all bits have been examined. Solution 1. Test case 1. Let's test our function using this input, 11. This number represents the value whose binary form we want to inspect. Our goal is to count how many bits in that 32-bit representation are set to 1. The number 11 in binary is 1011. If we look at those 4 rightmost bits, the first bit is 1. The second bit is 1. The third bit is 0. The fourth bit is 1. That gives us a total of 3 1 bits. Our loop checks 1 bit at a time, moves the number right, and keeps a running count, so it should return 3. And that's exactly what the program outputs, 3. And the expected result is also 3, meaning the solution works perfectly for this test case. So, our implementation is correct. The algorithm successfully counts each bit in the number using a simple loop, efficient and accurate. Now let's try another implement approach using solution 2. We begin by defining the solution class, the container that will hold our optimized method for counting the number of 1 bits in a number. This method, Hamming weight, takes an integer n and returns how many bits in its binary representation are set to 1. Here we initialize a counter C to 0. This will track how many 1 bits we find as we process the number. This loop runs as long as n is not 0. But unlike solution 1, which checks all 32 bits, this loop only runs once per actual 1 bit in the number. This line is the heart of the optimized solution. n equals n1 removes the rightmost 1 bit from n. Since we just removed 1 bit, we increment our counter C. This means each iteration adds exactly 1 to our total, 1 iteration per 1 bit. This ends the loop. We return the counter, which now represents the total number of 1 bits in the original number. And that's how this algorithm works. It first initializes a simple counter, then repeatedly strips off the lowest one bit of the number until nothing remains. Efficient, simple, and elegant. Solution 2. Test case 2. Let's test our function using this input, 128. This number represents a 32-bit integer whose binary pattern we want to analyze. Our goal is to count how many bits in that pattern are set to 1. Here's why the solution works. The number 128 in binary is 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 The trick used in this optimized solution is the expression n and equals n1. It removes the lowest set bit from n each time it runs. Since 128 has only one set bit, the loop runs exactly once. After removing that bit, n becomes 0, the loop exits, and the counter ends at 1. And that's exactly what our program outputs, 1. And the expected result is also 1, confirming that the bit removal trick works perfectly for this test case. So, our implementation is correct. The algorithm successfully counts the number of set bits by removing them one at a time. Efficient, accurate, and reliable. Alright, let's wrap this one up. This problem was all about uncovering the hidden ones inside a number's binary form. A perfect mix of logic and bitwise precision. Breakdown recap. We began by understanding that the task is to count how many bits are set to 1 in a 32-bit integer. It's simple in concept. Look at the binary version of the number and figure out how many ones are present. Assess recap. Next, we compared approaches. The straightforward way is to check each bit one by one, but that's not very efficient. Instead, we turned to Brian Cunningham algorithm, which smartly removes one set bit at a time using n and n1. This drastically reduces the number of steps, especially for numbers with few ones. Structure recap. The logic flow was clean and minimal. Start with a counter, repeatedly clear the lowest set bit, and keep counting until the number becomes 0. When it's done, that count gives the total number of 1 bits. Implement recap. We implemented this on LeetCode, and the solution ran smoothly without any errors. Check recap. After testing the code on multiple inputs, every test case passed, confirming the efficiency and accuracy of the approach. The key takeaway here is the elegance of Brian Cunningham's algorithm, a reminder that understanding bit-level manipulation can turn a brute force task into a lightning-fast solution.